So you can combine those two to obtain N of E. So what that tells you is, how many states do we have up to a given energy E? Now, what we want is this density of states. That is, how many states are available in a given range of energies. So again, let me draw this picture that I just took off. That is Px, Py. So you look at the total number of states inside this circle, that's N of P, and the P, of course, translates to a particular value of the energy, so that gives you N of E. Now, what is the density of states? Well, what you want to know is, if I increase the energy a little bit, like so, how many extra states do I get? Well, the way to think of it is, find N of E, find N of E plus dE. So this is the extra energy, and N of E is what's inside. And then if you divide it by the energy range, that will tell you the density of states per unit energy right there. So it is N of E plus dE minus N of E divided by this delta E. And this, as you'll note, is basically the derivative of N. So density of states, so my basic point is that the density of states then is given by dN dE. So that's the overall procedure then. If you're trying to write down the density of states, first question, what's the energy momentum relation? Next, write down this number of states as a function of momentum, and this is what I'll be discussing next in the next module in detail. Once you have N of P, you can turn it into N of E, and then if you take its derivative, that's what will give you the density of states. That's the D of E. That's it. And in the homework problems, we have a couple of different energy momentum relation for which I ask you to find the density of states using this procedure, and that should give you some practice as to how it works. And you can look at the video tutorial where I'll work out those examples. Okay. Now, right now, I just want to finish up this module with a short demonstration of a particular relation that should hold in general, irrespective of the energy momentum relation we use. And let me explain. So that relation, let me first state it. The relation looks something like this, that the density of states times the velocity at a given energy times the momentum should be equal to N is this number of states, times the dimensions. So this is a general relation that should hold irrespective of the energy momentum relations. Although, depending on the energy momentum relation, you might get a different density of states, velocities would be different, etc. But this particular relation should hold in general. And this is sometimes useful. And for this homework problem, what I ask you to do is, for a specific energy momentum relation, actually calculate D and show that this relation indeed holds. And again, you can look at the tutorial to see how that's done. But right now, I just wanted to explain where that relation comes from. And it's based on this idea that N of P is actually P to the power the number of dimensions. Because what we can do then is, we could write as, so density of states, as we discussed, is derivative of N with respect to E. So what I could do is write this as dN dP times dP dE. Okay. Now, one general relation that will be useful will come up later also, and that is that the definition of velocity is dE dP. Again, you can check this works easily if you have if E is P square over 2m. That is the usual case. But regardless of what energy momentum relation we have, it could be a complicated energy momentum relation, the definition of velocity in general is actually this dE dP. It's the rate of change of energy with momentum. And so this quantity is like 1 over V. Now, the next point to note is that as long as n has this form, p to the power d, we can write dN dP as d times p to the power d minus 1. So what that means is, again, I guess this is proportional. So let's say there is some constant here, A. So here also I'll put some constant A. A is just some constant we don't need to know. Now if I multiply both sides with P, we'll get d times A p to the power d, and that again is n. So the bottom line is that P times dN dP is equal to d times n. Now if I combine these two relations, then you'll get the relation that I stated over there. And let me just go through that quickly. Because this is 1 over V, you can see that d times V is equal to dN dP. And now, if I just multiply both sides with P, I'll put a P there and a P here. And then, the point is, P times dN dP is actually number of dimensions times n. So, this is equal to d times n. And that's the basic relation that I stated earlier. So this is a relation that, again, I didn't make use of any particular energy momentum relation, so it holds in general, regardless of the details, and it's often a useful relation that we'll be making use of later down in this week. But what we'll now go on to in the next module is, I'll try to explain how you obtain that constant, that is, this n of p, because once you have the number of states for a given momentum, this function, we can then, as I discussed, take any energy momentum relation and turn it into a density of states. And that's basically the concept we are trying to discuss this week.
Nano Hub U, online instruction.
So, welcome to module 2.2. And just to remind you what we did in module 2.1, is that, the overall objective of this week is to introduce a model for calculating this density of states. And in module 2.1, I introduced this simple model that we'll be using, which starts from this energy momentum relation. That is, given a solid, we know from experiments from other theory that electrons in the energy range of interest behave as if they have this a particular energy momentum relationship. So let's say that's given. What we are talking about is, from that energy momentum relation, how do I obtain a density of states? And as I mentioned, first step is to ask how many states do we have for electrons having all possible momentum up to a maximum value of p. And what I argued in that last module is that without going into any details, you'd expect that that quantity should depend on p to the power the number of dimensions. Because if you are in 2 dimensions, it will depend on this area of a circle whose radius is p, and so on. So that's this a, p to the power t. And we didn't talk about this constant in front, and we said, well, even without knowing that constant, the point is, what you see is the overall picture, namely n of p, you combine with e of p to get n of e, and then you take its derivative, you get density of states. Okay. Now, what we are going to do in this module is talk about how to obtain that coefficient that I wrote down. Now, consider just a one-dimensional conductor for the moment, and electrons can have any momentum, let's say, from minus p to plus p. There is a maximum value plus p, minimum value minus p, and we want to count the number of states. And basically, the number of states you count by saying that electrons can have certain values here, certain values of momentum, and one then tries to figure out how many of these allowed values are contained within this range. Now, classically, of course, the electron could have any momentum. So in that sense, the number of states would have been like infinite because it will be just continuously distributed. Now, the way you get a finite number is by invoking the wave nature of electrons. And this is the part that would come kind of naturally if you were using a wave equation for electrons, like the Schrodinger equation. And that's the kind of thing we discuss in the second course. Now, what I'll do here, though, is we'll use a very simple model to account for the wave nature of electrons. And that is this idea that you have, I'm sure you have heard of this in freshman physics, that electrons with a momentum p act as if they have this de Broglie wavelength. So I'll put a dB here to denote de Broglie, because after all, I've already used lambda for something that is physically completely different thing, namely mean free path. And this has nothing to do with mean free path. Mean free path is a classical concept. That is particles, how far they travel before they get scattered. This is a quantum thing. It's this wavelength of the electron. And this de Broglie wavelength is related to the momentum by h divided by p. So a given electron with a momentum p has a de Broglie wavelength given by this. Okay. And then the way you argue that momentum can only have certain values is by saying that if you have a box of length L, then you see the electron wavelength must fit into this box. Kind of the way classically, if you had, say, a guitar string. So supposing this, instead of being a box containing electrons, was actually a guitar string on which you could have acoustic waves. Then as you know, like on a string, usually you could have acoustic waves with any frequency or wavelength. But once you pin it down at the two ends, that's when the acoustic wave must fit into that length, which means its wavelength must fit into this box. And that's what gives rise to these specific values of wavelength, which translate into specific values of frequencies, which is why a guitar string has certain resonant frequencies. So, of course, electron waves are totally different from acoustic waves, very different things physically, but the math is kind of similar. The idea is kind of similar. And what you say is that the electron wavelength must fit into this box, and so we can say that the length of the box must be equal to some integer, I'll write that as nu, some integer times your de Broglie wavelength. So the length of the box is integer times the wavelength, because it must be, say, certain number of wavelengths long. Now, if you turn that around, we could write this as, from there, we could write it as P is equal to integer times H over L. So all I did was took the P up here, brought the L down there. And that tells me that the allowed values of momenta are integer multiples of H over L. So when I have a range of P's like this, the allowed values of P will all be spaced by H over L. That's it.